Morning all. The only thread in the topics that folk have asked for another look at so far is uncertainties. So let's have a look at some uncertainties information and then have a look at an uncertainties past paper question to see how we deal with them. Let's say we have a quantity called x. The uncertainty in our quantity called x would be delta x. And delta x over x would be our fractional uncertainty. This one doesn't come up too often, but it's on the road to doing other things, so we'll just mention it now. And then, of course, we've got delta x over x times 100 to make it a percentage uncertainty. So far, so good. So if we say for the sake of argument that our measurement x is 8 metres and the uncertainty in our measurement is 0.1 metres, then the fractional uncertainty would be 0.1 over 8, which should be 0.0125, and the percentage uncertainty 0.1 over 8 times 100, which gives us 1.25%. So 10, 100, 1.25%. Now for combining uncertainties, there's a bit of spherical coordinates and a bit of calculus involved in the why we do what we do, but for our purposes, all we're really interested in is what do we need to do. So if we have a quantity called, let's see, z, and z is some function of x and y, then delta z is going to be equal to, let's see, delta z over z is going to be equal to delta x over x squared plus delta y over y squared, and then of course the whole thing square rooted. So in most cases what we'll need to do is find this part here. We'll then, for each quantity involved in our final measurement, the result of our, usually it's an experiment setting for this question, find the delta over the measurement for each quantity involved and square away. And then add them up and then square root it, and that's you got the delta z over z for the final result. And then you just take that value, multiply it by z, and hey presto, you've got the uncertainty. There's a couple of little bits we need to consider. First thing we need to consider is just how significant is each uncertainty in the end result. Because if one uncertainty is less than 3 times the size, in other words, if one uncertainty is 3 times smaller than any others, it can be ignored. Now, why is this? Well, if it's less than 3 times the size of one, then the other one is logically 3 times bigger than it. And when you square 3, you get 9. So if it's more than 3 times bigger and you're squaring more than 3 times bigger, you're really talking about in the ballpark of 10 times bigger. In other words, an order of magnitude bigger. So that's a rule that we apply to make life simple. If we have an uncertainty that's less than 1/3 the size of any of the other uncertainties in our measurements, we can just ignore it because it's so small, it's not going to make a significant difference. Now, if like me, you like to be ultra cautious when dealing with uncertainties, you can simply perform any needed calculations to find the overall uncertainty, including any that are very, very small and could probably be ignored. That would not be marked wrong, that would simply be being a little bit overcautious. The other thing we need to be careful when considering is, what if our function of y and x that we're going to use to get z has a power in it? Well, if we have, for example, z equals x plus y squared, then in order to find delta z over z, what we need to do is first find delta x over x. Second, find delta y over y. Third, we need to allow for the fact that it's y squared. So to allow for the fact that it's y squared, we're going to make it 2 times delta y over y. And that's what we're going to use. So in this case, delta z over z is going to equal square bracket, curved bracket, delta x over x squared plus bracket 2 bracket delta y over y squared, close the square bracket, and square root the whole thing. And that 2, there's a bit of calculus that explains why we're doing that 2. You can probably guess where the calculus is. You've seen the pattern before. Take the 2 that's the power, bring it down to the front. But for our purposes, what we need to know is that's what we would do if there were powers involved. So here we've got a relatively simple example. We're going to use our old friends, the equations of motion, v squared equals u squared plus 2as, and simply picking numbers for the purposes of having an example. If we say u is 10 meters per second plus or minus 0.5 meters per second, a is 3 meters per second squared plus or minus 0.3 meters per second squared, and s is 20 plus or minus 0.01 meters. So first thing we do is get our delta u over u, which is 0.5 over 10, which is 0.05. Our delta a over a is 0.3 over 3, so that's 0.1. And our delta s over s is 0.01 over 20, so that would be 0.01, becomes 0.001, becomes 0.0005. Does that sound right? Yes, it does. Next step, are any of these three times smaller than any of the others? Well, 0.05, 0.005, 0.1. This one is 3 times smaller than this one. This one, however, is only twice as small as this one. So that means that, using the rule of thumb that we had previously discussed about 3 times smaller, we could, if we chose, ignore that one. It's so small in comparison to the others that it's not going to make a significant difference. Not ignoring it isn't wrong. Including it in the calculation for the uncertainty is not wrong. It's just being a bit overly cautious. It's like the old story of how many times do you measure the width of a doorway before deciding whether the chair fits through it or not. It's all about what's appropriate to the scale involved. And in this case, the uncertainty in the displacement is so small that it can effectively be ignored. But let's just work our way through the whole thing. So what we would do to find delta v over v is, open up our square brackets, delta u over u squared plus delta a over a squared plus, now if we're going to be overcautious, we can put in delta s over s squared, square root the whole thing, and then we've got, of course, that was a u squared in the formula, so we want to make that 2 delta u over u squared. And of course we could, if we chose, ignore that one because it's so small. But let's not. Let's just go through it step by step. Delta v over v equals square bracket 2 times delta u over u is 0.05, 0.05 squared plus delta a over a, 0.1 squared, plus, if we're not going to ignore it, which we could if we wanted to, 0.0005 squared, and square brackets. And notice that the fact that the u squared being a power of 2 and therefore requiring us to double the fractional uncertainty there means that actually the uncertainties here and here, when we're working with the calculation, turn out to be these two are definitely on the same scale as each other. Not at all safe to ignore either of these, but so small you probably could ignore it. So, according to my other iPad calculator, this is what we get inside the bracket before we apply the final square root, 0.02000025. So here we see why this 0.0005 squared is going to be so small, it's going to make no significant difference to the final answer. So, let's see what we get. Square root of that, and we get 0.14. So, delta V over V equals 0.14. And then, of course, what we need to do to find the absolute uncertainty is simply do the V squared equals U squared plus 2AS calculation with 10 for U, 3 for A, 20 for S. That will give us what V is, and then we multiply whatever that value is by 0.14 to get our delta V. Like so. Okay, so quickly running through the V squared is U squared plus 2AS calculation. 10 squared plus 2 times 3 times 20 should give us 220. But that, remember, is V squared, so square root that, we get 14.8 meters per second. Now, many of you will have noticed me being critical of intermediate rounding in the past, and that is why, using the beauty of the calculator and the memory function, I have not rounded off. I've written it off and I've written it down there, but I've kept the full digits in the calculator memory. So, I take that, I multiply by the value that we had when we square rooted, I get that, and so I'm now on 2.097, so I'm going to call that 2.10 meters per second. And then my final answer would be written as V equals 14.8 plus or minus 2.10. Really, I shouldn't have that 0 there if I'm going to write it this way. Meters per second. And there we're done. Okay, so now let's look at a typical past paper uncertainties question. This is question 11A from the 2015 traditional past paper. It is a student doing Young's double slit experiment in order to determine the wavelength of monochromatic light. We have a diagram of the setup, like so. The double slit separation small d is measured using a travelling microscope. The distance large d between the double slit and the screen is measured using a steel measuring tape. The length L of the interference pattern is measured using a plastic ruler. The student records the following data. So that is big D equals 4.250 plus or minus 0.005 meters. Big L is 67 plus or minus 2 millimeters. And small d is 0.25 plus or minus 0.01 millimeters. Oops, that should be there, not there. So the first thing we do is we work out the fractional uncertainties. So there is the fractional uncertainties worked out. And if you wanted them as percentage uncertainties, then again, I'll let you check the sums later on, but this would come out to be 0.12%. Just a little bit of a second decimal place in there. I've got a percentage uncertainty in delta L over L would be 3%. And the percentage delta D over D would be 4%. Now, that's going to give us, whether you present them as fractional uncertainties or as percentage uncertainties, and I'm just going to move this percentage sign over a little bit because I don't like it being over the line there. It makes it imply that it's being divided by L, which it isn't. Whether you do them as fractional uncertainties or whether you do them as percentage uncertainties, so far so good. We can see these two are in the same ballpark. This one is significantly less than any of the others. It's much less than a third of either of these. So for the purposes of doing our calculation, that one is so small, it's negligible. Therefore, our percentage uncertainty in our final answer is going to be 3% for this one, squared, plus 4% for that one, square rooted. And that's going to be, let's see, 3 3s are 9, 4 4s are 16, 9 plus 16 is 25, square root of 25 is 5%. So if we're going to be extra fastidious about our final presentation of the answer, we have got our final answer down here, 6.5 times 10 to the minus 7 plus or minus 3 times 10 to the minus 8 metres. If we really want to impress our marker and our examiner, we rewrite it as either lambda equals 65 plus or minus 3 times 10 to the minus 8 metres, or slightly less preferable but still correct, lambda equals 6.5 plus or minus 0.3 times 10 to the minus 7 metres. So this, putting it all onto the same order of magnitude on our powers here, makes it for a very easy comparison of the values in the brackets, which is more correct than this, but this is still correct if that is where you happen to stop.